piece of biological kit I'm using to talk to you now is one of the most remarkable organs we possess. I don't just mean my voice, which is a fairly average specimen I've always thought. I'm referring to that phenomenally complex piece of our shared heritage, the human voice, so familiar, so basic to our lives as social beings that we tend to take it for granted. Over the next 3 editions of Discovery here on the BBC World Service, I'm going to be finding out what the voice is, how we use it and respond to it, and I'm going to be listening with fresh ears, I hope, to some of the amazing sounds this natural instrument makes.
It's a tiny instrument in comparison to man-made instruments. If you were to take the part of us that really makes the sound and put it next to orchestral instruments, we would be alongside of the piccolo, among the smallest, and yet our frequency range and our loudness compares to many of the medium to larger sized instruments.
Is the person happy, sad, angry? The voice is really the best vehicle for emotion. And we are also very good at picking up these signals on the perceptual side that allow us to guess a lot of information on a person's affective state.
All of us can imitate various sounds. You can go around imitating the sounds of musical instruments, birds and dogs and things, with our vocal apparatus. So what we've actually got is a very versatile synthesizer for making different sounds.
It's only comparatively recently that scientists have started to pay much attention to what goes on in our throat when we make sounds. As you'll hear later in this programme, it was only with the invention of the jet engine that the passage of air through our voice box finally made any sense. Because although we all recognise its products, the larynx is a tricky customer, a closed tube resonating at different frequencies according to the tension we exert on the folds at one end. I could go on. Instead, I'll let leading voice researcher Ingo Titze of America's National Centre for Voice and Speech demonstrate.
If I were to go, in that continuum, I simply take my vocal folds and keep them somewhat more apart initially, and then I press them together. And if I were to press them excessively, at some point phonation would stop. Simply the air pressure couldn't separate the tissue anymore, and it would be essentially a complete shut-off.
How our vocal folds operate and how we operate them involves a process of internal muscle control every bit as complicated, although it's unconscious, as the procedures painstakingly learned by anybody playing a wind instrument, like a saxophone or a clarinet.
That process of setting the vocal folds into vibration, or we call it self-sustained oscillation, is a highly nonlinear process and a very difficult one to understand. It has taken us 20 years as scientists to sort of figure out under what conditions these tissues can vibrate and not vibrate. And keep in mind, the vocal cords are intended originally to be just a valve for allowing us to breathe and not breathe and protect the airway if necessary. So they're very much like an on-off switch. And as we begin to practice vocally and do all these wonderful things with our voice, we learn to make them into dimmer switches where they can gradually be used to put the vocal folds in very precise positions.
To better understand how the vocal tract works, I went to Stockholm's Institute of Technology to talk to Johan Sundberg, Professor of Voice Acoustics, whose lifetime research into voice production has led him to conclude that our larynx works pretty much like a duck call, a device known to Scandinavian bird watchers and hunters that imitates the quacking of a duck.
If you blow air through the duck call, you will get a pulsating airflow, and that is a sound.
And this looks a little bit like the mouthpiece of a clarinet or an
organ, it's the same principle. This is the sound of the duck call.
So that's the raw sound, and where does the sound then go?
That sound goes into a tube, the vocal tract, which consists of the pharynx and the mouth, and that is about 17 and 20 centimeters long. And if it were cylindrical, you get a vowel that sounds like this. So I coupled the duck call with a cylindrical tube of about 20 centimeters length, and you get which is and the odd thing is that this is what people say when they don't know what they want to say. But if you switch the cylindrical vocal tract to a deformed, non-uniform vocal tract.
And now you're fixing another more flexible looking tube onto the duck
sort
call.
of garden hose. So you could squeeze it in the one end, and you could squeeze it in the middle, and you could squeeze it in the front, and you could squeeze it in the middle and in the front. So I just blow.
You're basically mimicking with your hands on that tube the way in which we manipulate our vocal tract when we speak.
And then you could switch between a constriction at the low end and at the front end.
So, with apologies to ducks and duck lovers everywhere, that's how it is with the human vocal tract. It's a variable filter, accentuating different frequencies to order. The different areas we emphasise when we change the shape of our mouth or twiddle the folds in our larynx are known as vocal formants. Tecumseh Fitch of St Andrews University in Scotland studies the anatomy and evolution of vocalisation in mammals, and armed with a computer full of vocal formants, he showed me how formant frequencies allow us to create some of the key building blocks of human communication, vowel sounds.
You can think of them as little windows that let certain frequencies pass through while blocking out most of the rest of the signal. So what the demo that I'm about to show is essentially equivalent to taking a human vocal tract. So you can imagine taking my head and putting it on an animal's larynx, or on an animal's lung and larynx. And so what we're going to do is take this human speech.
Where in the hell are you?
And I'm going to separate the source and the filter. I'm going to separate the formant frequencies of the human, and now I'm going to add them on to this bison's roar. Okay, so now I've got the bison's source, the bison's larynx, playing through the human filter, and here's what we get.
Where in the hell are you?
Okay.
Where in the hell are you?
Let me give you another example of this. This is with a narwhal, so I'm going to take this narwhal and play it through a human formant function.
Where in the hell are you? Where in the hell are you?
So what you can see in both of these cases is that the human filter is what's imparting the letters, so to speak, the phonemes of the sound, but you can still hear the bison in the background or the narwhal in the background. The output of our mouths is actually a combination of the source and the filter, and both are present perceptually.
Computer software now allows researchers to separate and manipulate our sound source, the larynx, and the vocal tract which filters it. How the brain perceives the interactions of the two is a subject of great interest to the psychologist Pascal Berlin of Glasgow University. Mindful that he was talking to Discovery here on the BBC World Service, Pascal chose a speech sample he thought we'd recognise to make his point.
BBC World Service. BBC World Service.
So what you can do from that is put it through a software that will decompose it into these independent source and filter components. And then we can manipulate them independently. So if I manipulate them and I artificially reduce the size of your vocal folds and also the size of your vocal tract, the impression we are going to get is the impression of a voice produced by a female.
BBC World Service.
Now, if on the other end, again from your original voice,
BBC World Service.
if I do the reverse transformation, if I artificially enlarge both your vocal folds and your vocal tract, then the impression we're going to have is really of a much bigger person.
BBC World Service.
So these are the kind of types of information that we use in our everyday life to build a representation of speaker's voice and allow us to recognize, differentiate different types of voice. And for example, to extract information on the size of the person.
The extraordinary range of articulate sounds humans can produce has been believed to be down to the fact of our having a descended larynx. This is why we can do more with our voices than dogs, say, or chimpanzees can do with theirs. But biologist Tecumseh Fitch has recently discovered that we're not the only mammal to possess a descended larynx. Could this therefore confer some kind of evolutionary advantage on these non-speaking mammals?
We've discovered a group of different mammals. These include red deer, which live here in Europe, which have a permanently descended larynx. So this is much more similar to that of human beings. And it turns out that a number of different species have this. So this includes not only red deer and fallow deer, but also all of the big cats, so tigers, lions, jaguars, and leopards, and even koala bears. And there are some other species. So, for example, we've recently discovered that Mongolian gazelles also have a lowered larynx. So I wouldn't be at all surprised if there's quite a number of species who have this. And now we're talking about something that's much more similar to human beings and that clearly has convergently evolved. In all these different species, it's evolved for some reason. And in none of these species are they producing anything like speech. And that's where I think the story gets interesting, because it suggests that there's some other reason for a descended larynx that doesn't have to do with producing a wide range of formant frequencies. And our hypothesis in these other animals is that it's essentially a way of exaggerating one's body size, an exaggerated notion of how big an animal is. And I'll play you an example from a koala. This is a koala who's been run up a tree by some dogs. And I think you'll hear the contrast between the dog and the koala, who probably weigh about the same amount, very clearly when I play this sound. So if you ran into that koala in a dark alley, I think it's safe to say that you would have an impression that he was much larger than he was, and you might back away very quickly. And that, in essence, is our hypothesis for why these other species have evolved lowered larynx, that it's a way of, by lowering the formant frequencies, increasing the impression of size that the voice conveys. And in many of these species which vocalize at night, there really are no other cues to size. So having an exaggerated vocal cue to size could really be quite a useful adaptation.
You're listening to Discovery here on the BBC World Service. In the newborn human baby, the larynx has yet to descend. In this respect, a baby's voice acoustically resembles that of our closest cousin, the chimpanzee. But although its pitch is limited, the repertoire of sounds a baby makes is actually wider than it will ever be when the infant grows up. Our urge as babies to socialise, mimic and interact with our surroundings is extremely strong, and our mothers are programmed to cultivate it in ways that are not as soppy as they might sound.
Wiggly, wiggly, worm. Wiggly, wiggly, worm.
Talking to babies can be a strange business. We've all done it, using an unnaturally high register and elongating our vowels in a sing-song fashion. Alison Gopnik, author of How Babies Think, has studied this phenomenon.
When we talk to babies, all of us use this funny voice. So we all use this weird, high, squeaky voice. So we say, "Oh, aren't you sweet? You're such a sweet baby, aren't you?" As I'm saying this on the radio, all these miles away, I'm blushing. It's very hard to do this in cold blood.
So what freakish piece of mental hardwiring is it that instinctively turns us, when confronted with our offspring, into cooing sentimental idiots? Alison Gopnik again.
Well, it turns out that when you actually do acoustic analyses of that funny, strange, high squeaky voice, that high squeaky voice actually is beautifully, very sensitively, in a complex way, adapted to give babies just the information about language that they're going to need. The sound system of language is much more clearly specified in that strange, high squeaky motherese, as we call it, than it is in just everyday language.
Är du lite blyg? Pojke. Pojke.
Ulla Sundberg is the wife of Johan, the man with the duck call we heard from earlier. In her research, she's examined the ways that mothers modify their communicative behaviour to teach their babies.
Many mothers from many different linguistic communities, we all seem to do this. So we go very high up in the frequency and say, "Oh, yeah." And if you try to isolate different phonetic aspects in the signal and try to see what the infant is sensitive to, if you have these tonal aspects or duration or the amplitude, it's the tonal aspects. And the infants seem to prefer to listen to infant-directed speech relative to adult-directed speech. And in the infant-directed speech, you have these highly modulated intonation contours that you don't have in adult-directed speech.
But we're fairly sure that the infants like that, and that's not just something we're visiting on them for our own amusement.
No, we are sure about that. So the effects of all this is that the infant gets clearer auditory example of the vowel qualities and also a visual cue that is accompanied to the auditory signal.
The earliest influences actually seem to be on the prosody, so the intonation, the tone, the tune of the language, and those seem to be showing up in our data at least as early as 6 months.
That was Doug Whalen, a linguist at Yale University, who studied infants in Europe and the Far East to determine how the influence of the mother tongue, the surrounding language, affects the development of babies' voices.
So whether you end sentences with a rising pitch like you do in French or a falling pitch like you do in English, French just happens to have lots of sentences that end on a rising pitch. And English typically, or at least American English, has typically falling patterns, and we found this dissociation, as I said, as early as 6 months in our infants babbling. Some preliminary results we have for Mandarin indicate that the lexical tones of Mandarin, that is, using pitch changes within a single word, are beginning to show up about 12 months, but not as early as the intonational use of pitch.
12 or so years later, the human voice undergoes another change, this one akin to teething. With puberty comes a new, deeper vocal range. Petter Sjolander of Stockholm's Institute of Technology has conducted a rare study over several years looking at 60 boys at 6-monthly intervals and noting the way the pitch of their infant voices plunged from an average 220 Hz to 110 Hz.
We recorded a group of around 60 boys altogether, and we recorded them singing God Save the Queen. That was in the American choice, and it was a song they thought everyone would know. And what we did was we recorded these children and then took the recordings to analyse them to try to see if there's some kind of pattern that you can predict from when you start going into puberty to when you end and come out the other side. So we know that it takes 1.5 years, 2 years, but is it the same for everybody? And tracking these boys' speech and looking at how they develop over time and looking at the pitch difference. The biggest thing I've found so far is that you can put the boys into 2 categories. There's a before a major change and after a major change. There's a period when they're around 14 years where the voice really changes quite dramatically. And most of us have been trying to say for years that we mustn't call it voice breaking. We have to call it voice changing. That nothing breaks, nothing is affected, nothing happens that quickly. But my research is beginning to show that maybe things do happen quite quickly. There's a period in the middle where things change quite fast, and it's rather difficult for the boys to cope with that.
It can presumably be quite marked sometimes. For some people, they almost get a new voice.
Oh, yes, absolutely. Take the time periods away and play these voices with the same boy one after the other. You can hear such a change. You can't recognise the same voice.
God save our gracious Queen, long live our noble Queen. God save the Queen, Santa victorious, happy and glorious, long to reign over us. God save the Queen.
Does it often happen that boys or girls who've pre-puberty had what are considered to be beautiful voices end up with voices which are less beautiful as a result of the physiological change?
They maybe had this beautiful voice beforehand, but they don't necessarily have such a nice voice at the end of it because they've stopped singing. They have to use the instrument to be able to create the nice sound.
Well, that's interesting. So with their new voice, they're almost starting from scratch,
Yeah.
effectively.
Yeah.
So they have to learn everything all over
They
again.
would have to learn a lot of it, but other things happen as well. I mean, the vocal folds are still growing in the girls also, and the structure of the vocal folds changes. So there is quite a big difference between the children's vocal fold structure and what you end up with an adult. And many of these processes aren't finished until you're sort of in your mid-20s. So you're still using an instrument that's changing, even in your late teens and early 20s.
So what makes each of our voices unique? Something more subtle, apparently, than the shape and size of our vocal folds and vocal tract. It's all about patterns of airflow. Recently, voice researchers have begun turning to the world of aeronautics for inspiration, learning from the acoustic experiments of aeroplane engineers trying to reduce jet noise. At Cincinnati University, Sid Kosler has teamed up with the aero engineer Effie Gutmark.
When the airplane is flying, the interaction between flows of different speeds produces what we call vortices, which are places in the flow that have strong rotation of the air. The best analogy would be smoke ring embedded in a high-speed jet. Jet noise usually has low frequencies associated with this. There has high frequencies because large vortices produce low frequency noise and small vortices produce high frequency noise.
In terms of the larynx, it's basically a jet that's coming out of the vocal folds. There are airflow patterns in the vocal folds that produce an additional force for closing. And that's important for a lot of the sound that is in the higher frequency regime, or higher harmonics, as we say. And those higher harmonics turn out to be important for intelligibility. So, for example, people with Parkinson's disease, they won't close their vocal folds together fast enough, and that gives a soft voice, but it also gives decreased higher harmonics, which makes it harder to discern what they're saying because there's reduced intelligibility.
According to Sid Kosler, theoretical models have in the past shown how vortices affect sound production, but the Cincinnati team are the first to have used laser and camera technology to look at airflow in the mammalian larynx.
In order to see the flow, we need to seed the flow with some very small particles, micron-sized particles, and then a very thin laser sheath is then illuminating the flow for a very short time, and we take fast pictures of the pattern of these particles in the flow, and then with some kind of a mathematical processing, we can see the motion of tens of thousands of particles, and then figure out from that very complex flow field that is generated, the richness of vortices that are produced during the phonation cycle.
So what were you able to gather when you actually saw the airflow patterns in the larynx?
The first is we saw vortices within the vocal folds, and that causes a negative pressure which gives a rapid closing. And we know that rapid closing is important for high frequency sound energy, which is important for intelligibility. That was the first finding. The second finding is that when we looked at the three-dimensional structure of the vortices, we found that there are vortices in every plane, and that they're very repeatable, and they're very complex.
Okay, so you have patterns of airflow which are complex but form a distinct repeating pattern, but what effect do those patterns have on the sound of the voice?
When they interact with the walls of the vocal tract or the tongue or the palate, that will produce specific harmonics of sound. We strongly believe that those coherent vortices, because they're so repeatable, that gives the complexity or the uniqueness of my voice versus yours. And the key there, in a mechanical system, it's very difficult to produce something that is that complex and that predictable. And it's hard to duplicate in the mechanical models they build of a larynx.
The holy grail for voice researchers remains the artificial larynx. But ultimately, it's our individual and unique imperfections which make it so difficult to produce an artificial larynx which sounds human as opposed to robotic. David Howard of York University argues that this is because simulated voice boxes have aimed for intelligibility and accuracy above everything else. David demonstrated his point on a mechanical larynx he'd prepared earlier.
Now, if I place this on my own Adam's apple, but I close my larynx, I just hold my breath, so I don't vibrate my own larynx, I can talk with this.
Hello, my name is David Howard. I am speaking to you about singing.
So you get that kind of robotic voice, which is different to my own voice, but of course all the speech patterns are still there because they're formed in the same way as I am now by moving my tongue and jaw and lips. But the buzz at the larynx is completely different, it's mechanical.
And why but that doesn't sound like your voice, why not?
It doesn't sound like my voice because this hasn't got the characteristics of my own vocal folds. So this does not sound like my vocal folds. One thing that's different is this thing is electronic, and any electronic oscillator that's making a sound that changes in pitch will change in pitch in a steady, predictable manner. We know that the larynx doesn't do that. If you try to hold a steady note, ha, and you listen very carefully to that, it is varying, and I can't stop it varying. It's varying because human muscles are triggered by neural impulses, and the impulses never disappear. They're always there to keep the muscle going. And so there'll be little tiny twitches going on which will change very slightly the properties of the vibrating membrane such that their frequency changes. But the other thing is that any slight changes in the pressure of air from the lungs will mean that the vocal fold vibration will very subtly, cycle by cycle, be changing. And my own belief is that it's those subtleties of change that allows us to identify whether the sound we're listening to is natural, i.e. of human origin, or non-natural, i.e. of computer or electronic origin.
So, for now at least, the voice of a real person and its manufactured equivalent are easy to tell apart. Which is just as well, really, because in next week's Discovery here on the BBC World Service, I'll be investigating how we read and react to the voices of other people.